Hello, welcome to the pre-class video assignment for section 2.3. So in this section, we're going to be looking, at least starting to look at, how to solve non-homogeneous linear equations. Um, um, So in the previous section, we were looking at homogeneous linear equations, and we will need that information and need that ability to solve homogeneous linear equations here as well. But we're going to start looking at how the approach to solving something that is non-homogeneous. So in general, non-homogeneous means we have a function f of x here on the right-hand side that is non-zero. Again, this is sometimes called the forcing function, and we will talk about why that is called that later in the course. But basically, we're looking at a general second-order differential equation of the form like this. Now, as mentioned in the previous section, we do need to solve HEQs, homogeneous differential equations, in order to solve the non-homogeneous ones. There's some terminology here. When we are looking at a non-homogeneous equation, we will need the solution to the homogeneous equation, as we learned last time, comes from the characteristic equation of the homogeneous equation, or the so the homogeneous equation I've also referred to as being the associated homogeneous equation. So the characteristic equation of that homogeneous equation is called the complementary equation of the NHEQ. So that is some terminology we will see here as well. Shorthand, we denote it as Y sub C. So this should look familiar. This is sort of the form of the solutions that we were talking about in the previous section. Looked like this guy right here. They were, again, some constant C1 times a solution Y1 plus some constant C2 times a solution Y2. And again, we expected this sort of thing because as a solution to a second order DE, we were expecting two constants, a family of solutions involving two unknown parameters, C1 and C2. All right, in order to start talking about the non-homogeneous case here, we're going to first talk about under the conditions under which we have existence and uniqueness of an initial value problem. So in general, here would be a NHEQ initial value problem. So to a second order initial value problem, we'll have these two conditions, one condition on Y, one condition on Y prime. For our discussion here, we want to first manipulate this a little bit into sort of a standard form. So we would start by taking this DE here. We would divide everything through by P0 all the way through and rewrite our differential equation so that we have Y double prime and then a P of X times Y prime, Q of X times Y, and a little f of X on the right-hand side. And again, we still have the same initial conditions. So we've made this adjustment. So this would be what we want to do first before discussing existence and uniqueness. So there is an existence and uniqueness theorem. We will not be getting into the proof of it, as that is much more difficult, but it's not that difficult to understand or use. So a homogeneous, it says homogeneous, of course this should say non-homogeneous. A non-homogeneous second order linear initial value problem in this form will have a unique solution on any interval from A to B, open interval from A to B. Obviously, the initial value point must be contained inside that interval, but the conditions on the interval is that those three functions, P of X, Q of X, and F of X, must be continuous on that interval. So this is not too hard to establish. Given a non-homogeneous differential equation, I can simply look for where P of X, Q of X, and F of X are continuous, and then I can kind of pick the largest interval where those three functions are continuous that also contains the initial value point. So here's a little example. So here is our initial value problem. it is 1 minus x squared y double prime plus 3y, and then the forcing function on the right-hand side is 1 over e to the x minus 2, and here are our initial conditions at x is 0. Basically, we're starting our initial condition is occurring at x equals 0. So the first thing we have to do is convert it into this standard form. So I need it to be just y prime, hence I first need to divide through by 1 minus x squared. So that's my first step here. I'm going to rewrite the dE so that it looks like this. Notice that there was no y prime term in the original dE, so there was no p of x. P of x is going to be 0 here. But we have a q of x function and we have an f of x function that look like this. So we need to find the largest interval that contains the initial condition point at x equals 0, but does not contain any discontinuities of these functions. So if we look at q of x, clearly q of x cannot divide by 0, so q of x is not continuous. So again, the continuity of a function that is not piecewise and not absolute value, the continuity is its domain. It's continuous on its own domain. So it's really just a domain question. So here we can't allow x to be plus or minus 1. This would cause a discontinuity in the function q of x. So x cannot be plus or minus 1. Now we also have that condition for f of x. In f of x, x cannot be plus or minus 1, but we've already considered that. So the only new condition here is that e to the power of x cannot be equal to 2 ultimately. So solve that. That means x, take ln on both sides. X cannot be equal to ln of 2. X cannot be equal to it's about a 6.93 is what ln of 2 evaluates to. So probably the easiest thing to do here is just to picture this on a number line. Draw yourself a number line, doesn't have to be overly accurate or anything or plotted. I'm going to plot on my 3 conditions here, or my 3 discontinuities. Minus 1, plus 1, and ln of 2 is about 0.693, so that would be in here. So it turns out the plus 1 doesn't really enter into this. Our initial condition point is at 0, hence the biggest interval I can pick would be the interval between minus 1 and ln of 2. So this would be my interval of definition here. So there's a couple of little examples for you to try on my open math. It's the first one. And then there's a second one to try. Give those go. All right, so that's some of the basics. Existence of uniqueness, not a terribly difficult idea. Probably more importantly for us, we want to talk about the general solution for non-homogeneous equations. Again, we want to be able to come up with a general solution. So we're going to establish what that would look like here. So, all right, we're going to again start with our non-homogeneous equation in standard form. And then we're going to, just for saving ourselves some writing, we're going to write a little note, use a little notational tool. I am going to call it dE of y, dE acting on y, if you like. A lot of textbooks use L of y, or they usually use L, or maybe capital L, or a fancy script L of y. I have, in my math palette, I have a limited uses of capital L's here. There's only a capital L. I don't have any fancy script L's to use. We actually need to use L later in the book for something else. So I chose to call this just dE of y. Read this as simply saying the left-hand side of the dE. This says plug the function y into the left-hand side of the dE. That's all this is meant to notate. And by writing it this way, we can save ourselves a bunch of writing. All right. So we can say things like this. This is basically an abbreviated version of the dE. dE acting on y equals f of x. That is what this says. All right. So if just an illustration again, more about this notation, if the function y sub p of x is some known particular solution to this dE, then we can state that using this notation by saying if you put y of p inside the dE on the left-hand side, what you get out is f of x. That is stating that when we put y of p into the dE over on the left-hand side, we indeed get f of x out of it. So this is our notation. So this is a big deal. This is an important theorem for us. This is a big one. The general solution to non-homogeneous equations. So the statement says, suppose y sub p is a particular solution to a second order NHEQ on a particular interval AB. So imagine that we have found some particular solution, not a general solution, just any old particular solution to the second order non-homogeneous equation. Now, then also suppose that we can solve the associated homogeneous equation, and we have found two linearly independent solutions. So we call this a fundamental set of solutions. Then, this is the conclusion of the theorem, the general solution to the NHEQ is given by this. The general solution is y equals C1y1 plus C2y2 plus y sub p, basically. So recognize this guy here. This is the solution to the HEQ. This is the general solution to the HEQ, and then adding on any particular solution you might have found to the NHEQ makes a general solution to the NHEQ. That is the key idea. Again, it can be using the new notation and the new terminology we started with here in this section. The general solution to the NHEQ is the complementary solution plus any particular solution. Again, complementary solution was our new terminology for the solution to the associated HEQ. So we learned how to find y sub c in the previous section. In 2.2, we solved those guys. So we can find this. And so if we can find any particular solution to the NHEQ, then we can form a general solution to the NHEQ. So there's really two steps to solving the non-homogeneous case. You have to solve the associated homogeneous case and come up with this complementary solution to the general solution to the homogeneous case. And then you also have to go and find some solution to the NHEQ. Any of them, any one will do, just some particular solution. And then we form a general solution to the non-homogeneous by adding the two things together. Let's take a little look at the proof. The proof is actually pretty easy. It's sort of not obvious, but it's actually a fairly easy proof. So I kind of like this one. But let's assume that we have a particular solution. So let's suppose y sub p is a known solution to the non-homogeneous, and let's suppose that any other solution, so a general solution, if you like, any other solution to the same non-homogeneous equation, let's call that capital Y of x. Then what we have to show is that capital Y is yc sub yp. That is what this theorem states. So this is the proof, and it's kind of clever. Let's say, okay, so if y sub p is a particular solution, then applying the left-hand side, or substituting y sub p into the left-hand side, solves the NHEQ. Similarly, if big Y is a general or any other solution to the NHEQ, plugging Y into the left-hand side of the DE solves the NHEQ. Now, look at what happens when you apply the function or substitute the function big Y minus YP into our DE. So I claim that DE acting on Y minus YP, you can actually break this apart. This is DE of Y minus DE of YP. Remember, all that is required here to plug in to the DE is differentiation. Linear differentiation is linear. That is, you can differentiate term by term. So I can do derivative of y minus derivative of y sub p. So when we do that, clearly we get f of x minus f of x equals 0. Therefore, if this is 0, this shows that we've got a solution to the associated HEQ. So y minus yp must solve the associated homogeneous equation. So y minus yp is a solution to the associated HEQ. That means y minus yp is equal to the y sub c, or c1y1 plus c2y2, and then simply solve this for big Y. If you solve this for big Y, you get YC plus YP. Quite kind of clever, and actually not all that complicated. So this is our proof. All right, so a little example on my open math. So this is a multiple choice or a multiple answer. So it's the select all that apply situation. I am going to give you a particular solution to an NHEQ, and I'm going to ask you to select from a list what are the other possible solutions to the NHEQ. So apply these principles. You might need to refer back to how to solve for a complementary to solution to help you out, but take a look at that. All right, so that is where we're going to leave it for this packet in the video today. We're going to look at some prerequisites here in just a second. Again, we will finish this packet together in class. The big, hopefully obvious question remaining is, where does this y sub p come from? We need, in order to do this process, we already know how to find y sub c. We need to figure out where to find a y sub p from. And again, we are not fussy. It can be any particular solution. So that sounds like that shouldn't be too hard, but it is a little tricky. So we will talk about how we do that in the remainder of this packet and in the next section as well. Moving on then, some prerequisites that we will need to do this. Let's take a look here. So something we are going to look at for finding y sub p, a particular solution, is something called the method of undetermined coefficients. The method of undetermined coefficients, we will talk it all through, but there's a certain algebra skill here that I want to highlight and have you practice a little bit before we get there. And this is the idea of equating like coefficients. So again, a method we will be seeing to find a particular solution to a non-homogeneous DE is the idea is you actually going to make a generalized guess as to what you think the solution is, and then you're going to plug in your guess and try to solve. So a generalized guess. So my little example is, if you think that the solution to the NHEQ is a linear equation, then a generalized guess would be to plug in y equals ax plus b. Again, I'm using capital A, and usually books use capital A and capital B here. But if I then take this guy and substitute it into my DE, I can attempt to solve for capital A and capital B. So this can result in things that look like this. And of course, so here would be a simpler one with like a linear equation. 3 big A, 3ax plus b minus 4a equals 7x minus 2. Here's an identity. Here's one with trig functions in it. So when we do this, what we're going to end up with here are identities. These are not just equations we're trying to solve for x, or these are not just two functions, one on the left, one on the right, and we're trying to figure out where they intersect. That's not what we have here. We have a function on the left and a function on the right that are intended to be the exact same function. So these are identities, and this can help us solve because we can solve by equating like coefficients. So we will take a look at these little examples here. So actually, here's a simpler one still. If we look down here, if an equation like this is an identity, how can we solve this? Well, if it's an identity, the only way this can be an identity is if the a on the left, so this is an ax squared, that has got to be this term right here. Therefore, since the coefficient in front of the x squared is 1, a has to be 1. If there is no x on the right-hand side, bx, well, b has to be 0, and the c would have to be equal to the -4, right? If this is an identity, this would be how it has to happen. Again, the one up here is slightly more complicated, but not really. If you take a look at this one here, what we have is I have an x term on the left and an x term on the right. Those two terms must be identical, therefore 3a must be equal to 7. So 3a equals 7, a equals 7/3. Then on the other part here, we have, this is the constant term on the left-hand side. This would have to be the constant term, so this has to be the -2. So we would have b minus 4a must be equal to -2. So you can say b minus 4 times, we just found what a was. This is 7/3. So this would have to be equal to -2. So b would have to be equal to -2 is -6/3. And then adding this to the other side, there would be a plus 28/3. So this would give us 22/3 for b. So whatever that function was, if there was a linear function that we plugged in, the a was 7/3, the b was 22/3. So this is the idea of equating like coefficients. So give that a go here on my open math. The other example up above, so let's take a look at this one as well. We'll go all the way down here. This next one. This is, again, maybe looks a little strange, a little more harder to see, but again, once you see it once or twice, I think it's fairly clear. The point would be, what is what are the terms here? So here you have to understand that I might have to do a little distributing first. There's really a 2a x sine 2x. That is one term, and then I have a c times sine 2x, and then the other one I have a dx cosine 2x, and then I have an 2a plus, 2b, would have a 2b plus a cosine 2x. That is what I have basically on my left-hand side over here. That is what I have on my left-hand side. I really need to understand this as being 4 terms. There's an x sine x term, an x sine 2x term, a just sine 2x term, an x cosine 2x term, and a just cosine 2x term. So if we are equating to the other side of our dE here, I have an x sine 2x term. So basically we would have that the 2a would have to be equal to the -6 up here. There's no other way for this to happen, yes? There is no sine 2x term, so that tells us that the c is 0. There is no x cosine dx term. That tells us that the d must be 0. There is no cosine 2x term. That tells us that 2b plus a must be 0. So again, we can solve this fairly nicely. This means that 2a equals -6, a equals -3. And if 2b plus a equals 0 and a is -3, we have 2b minus 3 equals 0, 2b equals 3, b equals 3/2. So we have our solution. The c is 0, the d is 0, a is -3, b is 3/2. And again, so this is the idea of equating like terms to solve an identity like this. And this is a skill we will be seeing a lot of in this section and the next. So one more little example to try, or a couple little more examples to try, one with trig functions. And then another little example to try. This one has some other types of functions in, but hopefully you're getting onto the idea now. And that is it for this packet for today. We will, of course, finish the rest of it up in class together. We'll see you there.